Good afternoon, everyone. This is Professor Kuehn. You might recall in our last lecture, we were discussing Chapter 4 in a student's guide, where Sagredo, Simplicio, and Salviati are discussing falling objects. In particular, they're looking at the speed of falling objects as illustrated by swinging pendula. So just to remind you, imagine that you have two pendula that are the exact same length. Galileo considers pendula that are 4 cubits long, so it's just a string hanging from the ceiling with an object hanging from the end, and he considers the case where one of the objects is made of cork, so it's a light substance, and the other one is made of lead, so it's a heavy substance. And what Galileo found was that if you draw both of these back, so that they're starting at some initial position, some initial angle, let's say, and you release them, and you measure how much time it takes for the cork to swing back and forth, and how much time it takes for the lead pendulum to swing back and forth, those times are the same. It doesn't matter how heavy they are, and furthermore, it doesn't depend on, to a good approximation, it does not depend on the angle that they're pulled back to. So it seems to be that the speed, and this is how Galileo argues, the speed of a falling body, in this case it's a pendulum bob falling through some angle, the speed of a falling body does not depend on its weight. Of course, it does depend on how high you drop it from. So if you pull it back to a greater angle, let's say you take the cork one and you drop it from an angle of 1 degree, its speed going through the bottom is different than if you drop it from 10 degrees, its speed will be larger, okay? But the weight itself, if you pull these back to the same angle, the cork is lighter than the lead is heavier than the cork, and the speed with which they fall is going to be the same because they're falling the same distance in the same amount of time, okay? So this is the argument that Galileo is making. And so this raises a question immediately. So this is where we are continuing our discussion. This is review from the last time. So this is a review. Okay? And again, this is from A Student's Guide, Volume 2, Chapter 4. That's the context here. Now, if, as Galileo claims, there's this gravitas or gravity or heaviness that is inherent in all bodies, and their speeds do not depend on their weights when you drop them, then how, and this is Simplicio's question, I'll write this out in a moment, how, Simplicio says, is it true that a cannonball does in fact fall more quickly than a tiny birdshot made of the same material? So let me write that out. If gravity, gravitas, heaviness, gravitas, is inherent in all bodies, remember this is the view of gravity, it was sort of an internal heaviness that objects have. If it's inherent in all bodies, and he goes on to say, the speeds of falling bodies do not depend on their weight, as after all this was intended to show, the speed does not depend on the weight, then how, and this is Simplicio's question, if I remember correctly, Simplicio's question, then how is it that a cannonball, how does a cannonball, when dropped from a great height, a cannonball hit the ground before a birdshot, a tiny pellet of lead? So a cannonball made of lead or steel, if you drop a birdshot made of lead or steel, the same material, how is it that the cannonball hits the ground before the birdshot? And this is in fact true. Simplicio is pointing out a very important observation. Galileo is claiming that the speed of fall does not depend on the weight. Simplicio says, wait a minute, it does. You can actually go up to the top of a tower, drop a cannonball, drop a birdshot at the same moment, and the cannonball will hit slightly ahead of the birdshot. Okay? So this is a fact. Now, how does Salviati, speaking for Galileo, answer this question? So let's answer this in a couple of steps, okay? So first of all, we already know from the last chapter, chapter 3, we already know that a medium like air or water or whatever, a medium exerts a buoyant force. Oops, my tablet is slowing down. I have to pause for a moment until I can move my cursor. So exerts a buoyant force, which depends, so on a falling body, on a submerged body. So an upward directed buoyant force on a submerged body, which depends on the density with a specific gravity, the density of the medium, of the medium, the surrounding fluid, and the density of the falling object, the falling body. That's what we explored in the previous chapter. This was chapter 3. So there's this buoyant force that retards the acceleration. Okay, so you might think right away that this is going to somehow be able to explain the difficult issue that Simplicio brings up here. But Simplicio pushes us a little farther. And this, we're going to find, does not answer the specific question that Simplicio is raising. And we can show that in the following way. How, but how then, I'll phrase this as a question, then I'll try to answer this. How can we have two objects of the same material and hence the same density, falling through the same substance, the same medium, at different speeds? And this does happen. If this isn't clear to you, let me give you an example of what he's talking about. So this is, by the way, we're right around page 49 here. So imagine, to maybe sharpen this a little bit or to help you understand more clearly what's at issue here. Suppose you have water. So this is the medium. And suppose you have two stones. They're both made of the same material. One is a limestone boulder. Okay, so this is a limestone boulder, a big rock. Okay, and another one, this is a limestone grain of sand or a dust particle. So sand made of limestone, so basically powder, crushed up limestone. Okay, if you were to take water, that's the medium, and you were to drop this limestone boulder in water, and you were to drop this limestone sand grain in water, you would find that that boulder is going to fall with a very high speed, and that grain of sand is going to fall very, very slowly. This is why, for example, water can be murky, right? So if you're walking along in a pond and you kick up some of the sand on the bottom, the sand will scatter and form kind of a dusty particulate cloud in the water that slowly settles out, but the water will be murky for a while as it's settling. The tiny grains that are made of rock, presumably, will fall at a very slow rate, and it takes a while for the water to clear up. But if you take a large piece of the same material, a rock, and you drop it, it'll fall very quickly. So this explains, this is why water can be murky. It's precisely the issue that is being brought up here. Now, to show why this cannot be explained in terms of the density, remember that in the previous chapter we talked about the effect of buoyancy, is that the acceleration of a falling object is equal to the acceleration it would have in gravity, corrected by this correction factor, which is related to the density of the medium and the density of the falling object, right? So this was the effect of buoyancy, or buoyant force, on falling objects. Can this explain this effect right here? The answer is no, this cannot explain. So this cannot explain the above example. Why not? You might have seen this already. You might understand this already, but let me point it out to you. These two objects have the exact same density. After all, they're made of the same material. They're both limestone. You plug the same number in here. They're both falling through water. So they both have the exact same medium that they're falling through. So they should experience the exact same buoyant force. I should take that back. They're not feeling the same buoyant force. Their acceleration should be the same. The density of the medium is the same, the density of the object is the same, this factor is the same, and so the accelerations should be the same. But they're not. This one falls faster than that. So this alone cannot explain why it is that heavy, large objects fall in a medium more quickly than small objects. And this is the questions that's being raised here. If gravity is inherent in all bodies and the speeds of falling bodies don't depend on their weight, then how does a cannonball hit the ground before a bird shot? Or in this example, how does a boulder hit the ground at the bottom of the river before the sand grain? That's the question that's being asked here. And the answer to this, I'm going to briefly state it and we'll go into more detail next time. But how are we going to answer this is that the medium exerts drag on the surface of the object. And this is distinct from buoyancy. So the answer is that the medium, in this case water, exerts a drag force, exerts drag on the falling body, right? And the drag depends on the surface area. The drag depends on the surface area of the falling object. So because, and this we'll go into again this in more detail next time, because the surface areas are different of these two, they're going to experience different drags. And since the drag depends on the surface area, they're going to fall at different rates. What do we mean by drag? It's essentially a frictional force acting between the medium and the surface of the object that's falling. We know, by the way, that there is drag, and this is the example that Galileo gives, because if you take a lathe and you spin it very quickly, you hear a whirring sound. So, or if you took a stick and you whipped it through the air very quickly, you would notice kind of a whistling or whirring sound, and that, as Galileo explains, is the interaction of the air with the tiny, as he says, rugosities or bumps or dimples on the surface of the object you're moving through the air, and that is evidence of this interaction between the two. Okay, so let me stop there, and we'll continue this discussion next time.